Live from the Stability and Trim for the Ship's Officers podcast studio, where the vessel's its own best instrument of stability and trim. Welcome. This is William George. This is episode 20. We're at chapter 10 in Stability and Trim of the Ship's Officer. This is part 2, and we're talking about longitudinal hull strength. We're going to resume, if you have the book, on page 224, and we're probably going to go to page 232 today. So this is stresses on the loaded beam. And remember, we use simple beam theory when we're calculating and explaining hull stress. It is necessary now to investigate the type and intensity of stresses that fall upon the loaded beam. The theories of strength that result from a study of this kind is usually not only to arrive at the proper scantlings of an individual ship's members, frames, beams, and girders, etc., but also used to arrive at the strength of the entire ship's hull. In the later case, the entire hull of the ship is considered a single girder, and the strength of the hull girder is calculated by using beam theory. All stress on a loaded beam results from the differences in the forces on the weight moving in one direction and the resistance or support operating in the opposite direction. We're talking weight versus buoyancy. If no difference exists, no stress exists. The study of stresses on a loaded beam must start with the investigation of the differences in the weight and support. Find the types of stress resulting, and then find the intensity of these stresses. There are, of course, an infinite number of possibility in weight and support. Some of the simpler variations will be investigated. Consider first a simple rectangular beam loaded in such a way that the supporting forces are less in the middle of the beam than the forces of weight. The force of support are the greater than the forces of weight at the ends. And this is in figure 10-5, which is on page 226. And if you don't have the book, it's showing a beam where the middle is lower than the ends. And it also shows a neutral axis where there is no compression or tension. So in this case, there'd be tension at the top, compression at the top and tension at the bottom of the beam. So the beam will obviously bend. The upper and lower surfaces of the beam are now curved, but are still parallel with the ends of the beam are no longer parallel. Tangents run through the ends of the beam, which meet at a point above the beam. This point will represent the center of curvature of the upper and lower surfaces of the beam. It is obvious that the upper surfaces of the beam has been shortened and the lower surfaces of the beam lengthened. It is equally obvious that there must be a surface halfway between the upper and lower surfaces, which is the same length. This surface is generally designated as the plane of the neutral axis. In this case, all material above the neutral axis must have been in compression and below the axis in tension. Also, the stresses of tension and compression increase as the intensity as distance from the neutral axis, reaching their maximum at the topmost and the lowermost fibers of the beam. Another type of stress also develops when a beam bends or tends to bend. Since the force of tension and compression vary from the top and bottom of the beam, shear force must be in operation at the neutral axis. This stress, which is a shear stress, results from the parallel but opposite forces above and below the neutral axis. The aforementioned stresses of tension and compression and shear are all integral stresses on the beam. These stresses are the result of external stresses imposed on the beam, causing it to deflect or bend. If no deflection occurs, there will be no internal stresses due to loading of the beam. What causes the deflection of the beam? The external loading of the beam is the difference between the upward support of the beam and the downward weight of the beam, with any concentrated weight that may be present. In Figure 10-5, consider the center of the beam to have a concentrated load and the majority of the support of the beam at the ends. This causes external vertical shearing stresses on the beam, which result with the beam having a tendency to bend. A measure of this tendency is known as the bending moment. When there is a maximum bending moment, there will be a potential for a maximum deflection or bending of the beam. The tendency of the loaded beam to bend, then, is a function of the amount of weight and the distance of the weight, its center of gravity, from the ends, or from the intermediate supports. A force acting through a distance is called a moment, in this case, a bending moment. From the above, it should be apparent that the reason for constructing a structural shapes in the form of I-beams is to place as much of the material in the beam as possible at the upper and lower surfaces, or flanges, where it will do the most good in resisting bending. However, the flanges must be connected by an adequate web, which is the vertical part of a I-beam. While the external loading of the beam results in bending or a tendency to bend, and thus the internal formation of tension, compression, and shearing stresses, the tendency to bend will also vary with 1. The distribution of weight on the beam, whether uniform or concentrated, and uniform distribution creates less than a bending tendency. 2. Fixity of the end connections, or are the ends free to move? A beam may merely rest on a support at its ends, simply supported, or it may be fixed rigidly in place, fixed-ended support, by use of brackets. Fixed-ended supports create less bending tendency in a beam. What limits the beam to deflect? When a beam is loaded and the tendency to a beam created, the fact that the beam does not bend or bends only slightly implies an equal resistance to movement, which restores equilibrium. Resistance to bending in a beam is supplied by two forces or factors: the strength of the material of which the beam is made and the geometric form of the beam. For example, a wooden beam certainly would not be as strong as a steel beam. Steel is basically 30 times stronger than wood. As it has been stated, a beam formed in the shape of an eye offers more resistance to bending than a simple rectangular form with the same cross-sectional area. The latter factor of geometric form is measured by the moment of inertia of the beam. The total moment of inertia of the beam is made up, theoretically, of an infinite number of moments acting about the neutral axis of the beam. Each of these internal moments is made up of the resistance of tension and compression offered by each infinitely small unit of cross-sectional area of the beam multiplied by its distance from the neutral axis. Since resistance must always be exacted equal to the stress to achieve equilibrium, the resistance of each one of these infinitely small units is considered an equal to the stress existing at the unit. Moreover, the stress increases uniformly with the distance from the neutral axis. Therefore, to find the total moment of inertia of a beam, the cross-sectional area of each small unit must be multiplied by the square of its distance from the neutral axis to obtain the sum of these moments. The area of the multiplied by its distance from the neutral axis, once or the distance that the resistance is acting from the neutral axis, and once because the resistance itself is increasing uniformly with the distance from the axis. In this text, the moment of inertia is designated as I, which would be, if you look at it, a capital I that is italics. You do not need to be involved with the computation of I, but you do need to know that the larger the value of I, the moment of inertia, the greater the beam's tendency to resist bending. SM, section modulus, is the beam's geometric resistance to bending. With a given cross-sectional area to work with, it would be impossible to calculate two separate section moduluses for each beam above either side of the beam's neutral axis. One side of the beam would have as much greater I than the other because of a greater distance of its flange from the neutral axis. Thus, the distance of the extreme upper flange or the lower flange to the neutral axis is an indication of the efficiency with which the flange can resist these stresses. This distance from the extreme edge to the neutral axis is designated as, it's a lowercase italics y. If the moment of inertia I is divided by y, the result is an expression of I divided by y, which can be used as the modulus of the ability of the section, or the section modulus, to withstand not only bending but tensile and compressive stresses as well. Section modulus is strictly a geometrical consideration and hence it can be calculated in advance for all standard shapes and listed in handbooks on strength of materials. The units of section modulus are inches cubed, feet inches squared, or feet cubed in the imperial system. Remember, I would be units to the fourth power, y would be units to the a single distance. So when you divide something to the fourth power by a single unit, you'll get a cubic unit. So section modulus would be in basically the form of a cubic measure. For unusual built-up shapes or for a hull girder of a ship, section modulus must be calculated by calculating the moment of inertia I. Then I is divided by the distance from the extreme upper flange or lower flange to the neutral axis to build up the shape. What is the strength equation? As indicated above, the geometrical distribution of material in a section is a measure of its strength of the section. It is obvious, however, that the material used in the section also determines the strength of the beam and girder. The greater the strength of material, the greater will be the resistance to bending. Now it is known that the resistance to bending implies stress, that is, if a loaded beam does not break, it's obvious that the stress has been opposed by an equal amount of resistance. The maximum stress occurs at the upper and lower fibers of the loaded beam. The maximum stress is designated as small p, lowercase p. Thus, if you combine section modulus, which is I over y, divided by y, and p, which is the measure of resistance offered by the material of which the beam is made, then I over y multiplied by p, the resistance, represents the total resistance to bending, M, which is the bending moment. Since an external moment tending to bend the beam or girder is equal to the moment tending to resist the bending, M. So in page 228 we show M equals I divided by Y times P, where M is the maximum allowable bending moment, I divided by Y as the section